So we're still in chapter 5 talking about polynomial and rational functions. So last section we talked a lot about polynomials, so we're going to move on and talk about properties of rational functions. So the first thing we're going to do is find the domain of a rational function. And you'll see that that leads right into find the vertical asymptotes of a rational function. And then we're going to find the horizontal or, if there is one, the oblique, also called slant asymptote of a rational function. So let's define this creature. A rational function is a function of the form, and we use capital R to represent it. It's a ratio. See how the word ratio is right in there? It's a ratio of a polynomial over another polynomial. So P and Q are polynomial functions defined in the last section. And Q is not the zero polynomial. That would be a problem. And then the domain of a rational function is a set of all real numbers except those for which the denominator Q is 0. So all the real zeros of Q. So you see how this ties into the previous section. So we're going to continue to focus our interest on denominators when we're talking about domains. If a denominator equals 0, then a rational function is undefined. So this first function, you can easily see that if x plus 3 times 4 minus x equaled 0, that would be a problem. So we use the zero product property to see when does that happen. So when x equals -3 or 4, so the domain is actually x doesn't equal -3 and 4, because those are the places where we'd have a problem. So we'll do number 20 together in class. And this is just a little fine point, but it's an interesting example of the domain of this function is x can't equal -2, right? But let's factor the numerator and see that it factors to x minus 2x plus 2, or the other order if that's how you learned it. Well, this is a function, so we can't just cancel the x plus 2's because then we have a different function. But it turns out that the function, let's call it g of x, that looks like x minus 2. These two functions look almost the same, except when x equals -2. So this g of x is a graph of a line, right? In y-intercept of -2, slope of 1. So this is g of x. But then when x equals -2, there's a hole in the graph of r of x. So the graphs look almost exactly the same, except the r of x graph has a hole in it. So the domain of a rational function has to be found before writing the function in lowest terms. And let's think about, what does lowest terms mean? When a fraction like 6/8 is not in lowest terms, how do you reduce it? Well, you probably do it in your head without thinking about it anymore, but really technically what you're doing is you're factoring the numerator and factoring the denominator, and then you're saying 2 over 2 equals 1. And multiplying by 1 doesn't change anything, so that's why we cancel. And we're saying the factors that match in the top and the bottom become a 1, and multiplying by 1 doesn't do anything, so we can make them go away. So consider a polynomial. Let's see. How about the polynomial x squared minus 5x minus 6 over x minus 3? And is it in lowest terms? And how would you decide? Well, you'd need to factor the numerator and see that there are no matching factors in the top and the bottom. So this is in lowest terms. But what if I had x squared minus 5x minus 6 over x plus 1? Then you can see that this is not in lowest terms. So you have to factor to figure that out. When a rational function is in lowest terms, then real zeros, if there are any, of the numerator will be x-intercepts of the function. So in this example we just looked at, let's look at f of x equals x squared minus 5x minus 6 over x plus 1. It's not in lowest terms yet. So let's find the function that's the equivalent. So I have x minus 6, x plus 1 over x plus 1. So the function g of x, that's x minus 6, the graph looks almost exactly the same except at x equals -1. This is in lowest terms, and it has a numerator if you like. So when x equals 6, that is an x-intercept of the graph of this rational function. So here's another function we need to add to your library of functions. Let's think about how it has to look. Let's see, if I take x and square it, always positive. Reciprocal of a positive number. So that means y is always positive. So we only need quadrants 1 and 2. X can never be 0. So in fact, we get a vertical asymptote at x is 0. There can't be any graph there. Then when x is large, y is tending to 0, right, as you divide by a big number. Then when x is getting really small, close to 0, like a half, y is getting big. And then we can see it's an even function. So see how handy that is to notice? So we know it's symmetric about the y-axis. So we can use transformations to work on that graph. So here we have before the function happens, or inside the function, x plus 2. So that's going to shift 2 units left. Then the function happens, which is squaring and reciprocal. Then we have multiplying by 2, so it's going to be a vertical stretch by a factor of 2. And let's look at number 43 in class together. That one's a little trickier. Okay, so vertical asymptotes. If we draw the graph of this function using transformations, we see that we're going to shift right 1 unit because of the -1 before the reciprocal function. Then we're going to have a vertical stretch by a factor of 3. And then we're going to have shift up 2 units. Okay, so let's look carefully at what happens near x equals 1. So we're going to look at a little bit of limit notation, because this will come up in calculus, and so it's good if you're familiar with the limit notation. You read this here as the limit as x is going to 1 from the left. So this is the limit as x approaches 1 from the left. That's the meaning of that little minus symbol. So we're looking at a graph and we're saying x is approaching the number 1 from the left. And we're saying what happens with this graph when that's happening. So I like to use actual numbers, and I say, let me use a number like 0.9. Okay, so if I put 0.9 in here, 0.9 minus 1 is negative 1/10. So this is going to be negative 30 plus 2, so I'm going to get negative 28. So I can see that it's heading down towards negative infinity as I get closer and closer to 1. Like if I do 0.99, then I'm going to get an even bigger negative number, plus 2. So we're heading towards negative infinity in this case. So then if we approach 1 from the right, now we're approaching 1 from numbers a little bigger than it. So say 1.1. Well, if I do 1.1 minus 1, I get a 10th. Dividing by a 10th is like multiplying by 10, and I'm going to get 32. And then if I do 1.01, I'm going to get even bigger number, so I see it's getting bigger and bigger and bigger. Now, since these don't agree, we say that this limit does not exist. If they agreed, then that would be the limit as x approaches 1. Okay, so as x approaches some number, let's give it a name. Use the same one as your book. If it approaches some number c, the values of the rational function, if they go to negative infinity or infinity, then the line x equals c is a vertical asymptote. And you never have to write that out again. You can use VA. So if the limit as x goes to c is plus or minus infinity, then x equals c is a vertical asymptote. So in our previous example, we have a vertical asymptote of x equals 1. And we could see that because of the denominator. Okay, the other important feature of rational functions is their horizontal asymptotes. But I'm going to do that in a separate movie so that I don't rush.